Okay. I did a mic check already. Video seems pretty good. Um, I'm gonna do a share screen check in a second, but this recording is what you call a virtual I do. Normally it'll be done in a regular classroom setting with a whiteboard and a smart board in place where you can actually see the video that I'm about to present. I'm hoping that the sound quality comes through quite well as I'm going to switch the audio and video connectors or devices so you can hear it from the surround sound of a TV I have connected to the laptop. So with that said, this video is primarily an emphasis video and I'm going to share it in all of the student accounts within your classroom settings in SB. Uh, that's physics, third and fourth period, as well as your robotics and computer science students. Now, robotics and computer science students, I need you to pay attention to this because I'm also going to demonstrate the difference between a transformer and a generator. And all of you guys in that class have to deal with robotics to a certain point, point where you have to understand the rotations of the wheel, and that is a form of a motor and generator. And we'll discuss that later on in our own, because I'm going to generate videos towards understanding power electronics. But you will also need to explain in terms of why that phenomenon can be, in one instance, a form of work, and another instance, a form of generating power. So that's motors and generators. We'll try to discuss that in greater detail with the FET simulation a little bit. A couple of questions. I expect this video is going to run about maybe an hour to an hour and a half. So let's jump into it. I'm going to start with the first segment, which is about maybe 10 to 15 minutes, I want to say, of a professor and physics or physicist, because my heart enjoys electrical engineering and physics. So he's a physicist out of New York. He's well respected, like Neil deGrasse Tyson and others that I've watched since I was an undergrad, and gave me a glimpse into where they were going in the frontiers of science, like Carl Sagan, Richard Feynman, people of that nature. One second, please. All right, so with that said, I'm going to play this short video. Like I said, it's about 10 to 15 minutes. I'm not sure how long, but it's essential for the robotics and computer science students, the exploring computer science students, because you will have to, from the robotics student side, understand what the motors do with the robot. From the computer science students aspect, you will need to understand how to program the robot. So you got to know what you're programming, because the rotations that you make for a wheel inside of a first tech challenge that we've done before, when the classroom was open before this situation, um, those were the motors you were programming. That's why there was a programming team, and then there was also engineering, I would call it, team, pre-engineering team, because that's what robotic students are, CTE. And they would do the hands-on parts, putting the actual motors on the robot and everything. But there's a caveat to how motors function. They can also become generators. And that's why I want you to pay attention to this short video. If you can't hear through the sound quality, let me know in SB as a message. And basically I'll send you the whole video. But the reason I'm showing it this way is I can show you the samples that I want you to see, because a lot of students are saying, I can't see the video. So I'm gonna play it with you. I'm gonna share screen and change audio conditions so you can review it. So after that, I'm gonna go into the problem that was assigned. Second, I recently assigned it. It's from Monday, actually. Basically the 18th of May. So that's tomorrow. So I wanted to get this out there so there's no confusion. And then also there will be, GGIs where you get extra credit if you participate. And these are social skills. So you guys, this is mandatory for you to, especially for you seniors just trying to graduate. And also that same Monday around 1 to 2, I'm having a session on Google Meets where you bring your questions about any of the problems, as I've been doing. And thank you to the students, before I get off track, thank you to the students that's actually been looking at my handwritten solutions to problems and trying it out. I've given you credit for that. That's initiative. So I know we're all going through trying times, but I've seen you actually do the problems, type it up in the format that I'm asking, Google Doc to PDF, send to me under your assignment. you've been doing that. So thank you to those students that have been doing it. Keep that going, because that will help you get out of class, because you're learning the routine of how to submit actual assignments when they're dated. But with further delay, let me change screens and we're gonna go into it. So give me one moment to set up all the settings or make calibrations for you. So I share screen. Here we go. And I think right now they should be seeing what I'm seeing. All right, on screen 2. And next, I got to make sure you can hear it. So I'm not sure, audio doesn't, I'm not sure comes through Zoom yet. So let me change the microphone from mine's. That way the microphone should pick up the environment. And also, where did it go? Video settings. I think everything is set. Okay. So I don't need this at this point, because it should be there. I'm looking for a sound level check. Okay, I hear that. And then testing. Good, okay, and it sounds good because my mic is far away. All right, so now, we're gonna start at 13:54 of the video. So if you happen to not, got feedback. Okay, that's because the recorder is checking this out. All right, so we're gonna start at 13:54 because that's exactly where I want to start. This is a pretty long video. I think you can see my screen. It runs about, not all your day, but at least 42 minutes. And for those of you, students that's trying to understand where I'm going with robotics and computer science, again, I'll be bringing this up when I show you simulations, and as there's a question in there, and I'll explain it, but I'll see who can give in their own words, a response to the wonder of what's a generator and what's a motor. How does that work? If you ever pay attention, you have a motor from any RC type of car, you can reverse the way the motor is supposed to go, and you'll see some lights flicker in the device. So we're getting into transformers, electrical engineering and such, but I want to keep it focused on high school mathematics you need for physics. So let's jump into this video. I wonder if that works the same. We'll check on the playback. And
Aristotle's law of motion. Aristotle said objects in motion eventually stop because they get tired. The second law of motion says force is mass times acceleration, and that equation made possible the Industrial Revolution. Steam engines, locomotives, factories, machines, all of it due to the mechanics set into motion by Isaac Newton's second law of motion, force is equal to mass times acceleration. And then Newton had a third law of motion. For every action, there's an equal and opposite reaction. That's the law of rockets. That's why we have rockets that can sail into outer space. So the lesson here is, when scientists unravel the first force of the universe, gravity, that set into motion the Industrial Revolution. A revolution which toppled the kings and queens of Europe, which displaced feudalism, ushering in the modern age, all because a 23-year-old gentleman looked up and asked the question, does the moon also fall? When I was a kid growing up in California, I would see pictures of the Empire State Building. And I said to myself, how could they possibly build such a big building and not know that it's going to fall? Why doesn't it fall? They didn't build scale models of the thing. You couldn't have an Empire State Building that big to test whether it's going to fall or not. How did they know ahead of time that that building wouldn't fall? And the answer is Newton's laws of motion. In fact, today I teach Newton's laws of motion, and you can actually calculate the forces on every single brick of the Empire State Building. Using Newton's second law of motion, force is mass times acceleration. When Newton unraveled the force of gravity, that was the first force. Now let's take a look at the second force, an even greater force, which has touched all of our lives, and that is the electromagnetic force. Ever since humans saw lightning bolts light up the sky, ever since they were terrified by the sound of thunder, they've been asking, do the gods propel lightning bolts and create thunder? Are they angry at us? Scientists begin to realize that the lightning bolts and the thunder can be duplicated on the Earth, that we can actually create mini lightning bolts using electricity. But it wasn't until the 1800s that finally we began to unlock the second great force which rules the universe, the electromagnetic force. Michael Faraday would give Christmas lectures in London, fascinating everyone from adults to children. And he would demonstrate the incredible properties of electricity. Some people, for example, ask a simple question. If you're in a car or an airplane, you get hit by a lightning bolt, why don't you all get electrocuted? Why don't you all die? Well, Faraday answered the question. He would create a cage. He would walk into the steel cage, electrify it, and he wouldn't get electrocuted at all. That's called the Faraday cage. And every time you walk into a metal structure, you get shielded by this metal object. But what Michael Faraday did was, he helped to unleash the second great revolution with something called Faraday's law. A moving wire in a magnetic field has its electrons pushed, creating an electrical current. That simple idea unleashed the electric revolution. And that's why we have hydroelectric generators, dams that can produce enormous amounts of power. That's why people build nuclear power plants. That's why we have electricity in this room right now. On a very small scale, you use that in your bicycle. When you put a bicycle lamp on your bicycle, the turning of the wheel spins a magnet. The magnet then pushes electrons in a wire, and that's why electricity lights up in your bicycle lamp. So in other words, electricity and magnetism were unified into a single force. We once thought that electricity and magnetism were separate. Now we know they are, in fact, the same force. So if a moving magnet can create an electric field, this means that a moving electric field can create a magnetic field. But if they can create each other, why can't they oscillate and create a wave? So that moving electric fields create magnetic fields, create electric fields, create magnetic fields, infinitum, to create a wave. Well, around the time of the American Civil War, a mathematical physicist, James Clerk Maxwell, calculated, using the work of Faraday, the velocity of this wave. In one of the greatest breakthroughs of all time, James Clerk Maxwell calculated the velocity of this wave and found out it was the velocity of light. And then he made this incredible discovery. This is light. That's what light is. It doesn't by accident travel at the speed of electricity. It is light itself. And the equations were written down by James Clerk Maxwell. Unfortunately, Michael Faraday himself did not have a formal education. He could not put into mathematical form his own work. James Clerk Maxwell was a theoretical physicist, just like myself. He wrote down the mathematical physics of oscillating electric fields and magnetic fields, and they are called Maxwell's equations. These equations have to be memorized by every physicist in grad school. You cannot get your PhD without memorizing these equations. Every engineer who deals with radar and radio has to memorize these equations. And so, if you go to Berkeley, where I got my PhD, you can buy a t-shirt which says, "In the beginning, God said, the four-dimensional divergence of an antisymmetric second-rank tensor equals 0, and there was light." Ladies and gentlemen, this is the equation for light. The consequences of the electromagnetic revolution touch all of us. This is a picture of the Earth from outer space. Look at this picture. Europe, electrified. You can actually see the fruits of all of our efforts to create electricity to energize our lives in one picture, seeing the Earth from outer space. So let's now talk about how Faraday and Maxwell's work touches your life as well. This is the internet. The internet is a simple byproduct of the electromagnetic force, and you can see that where there is the internet, there's prosperity, there's science, there's entertainment, there's economic activity. Where there's no internet, there's poverty. And in the future, the internet will be miniaturized and it'll be placed in your glasses. Your glasses will recognize people's faces and display their biography next to the image as you talk to them. And then when they speak Chinese to you, your glasses will translate Chinese into English and print out subtitles right beneath their image. So in the future, you will know exactly who you are talking to without even talking to them. And this means that at a cocktail party, if you're looking for a job, but you don't know who the heavy hitters are, in the future, you will know exactly who to suck up to. In the future, chips will only cost a penny because we can manufacture tinier and tinier transistors. You will have Faraday's electromagnetic force inside your body. This is a pill. It has a chip in it. The chip is smaller than an aspirin pill. It also has a TV camera and a magnet. When you swallow it, the magnet guides the camera, pictures of your stomach, your intestines, because we all know what middle-aged men fear the most, colonoscopies. And this gives new meaning for the expression Intel inside. Now, let's talk about the...
Okay, so fix this. Okay, so I think everybody can hear me now. I'm going, I did a solo mission meeting because I wanted to have this as pure I do. And again, students, you can come back to me and we can do a session on Google Meet to talk about what's going on. But let's get into this because that's pretty much all I wanted you to view the video. Again, the video is about 40 to 40, you just say 45 minutes because you got to review it a few times. I'm not sure. But let me switch screens, do that. All right, so at this point, this video, and I want to come back to not sharing because I want to get the screen ready. Oh, stop share. That's why I like working with the system. All right, and so at this point, he's getting into the nature of, I don't know if you saw the bicycle portion of the video, where when you ride your bicycle, old school bicycles, when I was in Switzerland, we had to ride bicycles. And I understood what was happening when I was riding a bicycle and my light worked, the back and the front, because of that process he discussed. And then the internet too, as well as the facial recognition part. And I've told you all about that, how we have optics, biometrics, how people have signatures. So all this is going to computer science and robotics students. I hope you're paying attention to that, and I'll bring it up later. But I'm going to get into something that's very interesting about today's, or not today's, tomorrow's Do Now. And this is discussing three things. And I made notes so I can cover all of this in one session, and anybody that missed this session can review it. So basically, you have to discuss Ohm's law, which is something I've discussed a few times. I discussed it in the previous Do Now, where I had you using Ohm's law in a certain way. It was more mathematical. Like you had delta in there, and that's displacement. But now it's discussing how Ohm's law works with electron flow, right? Electron flow is a little bit different from traditional flow because you go positive, negative. But electron flow, you're going from positive, coming back to positive and down, out through negative. So that, you know, at the high school level, just want you to focus on positive or traditional flow of currents. So you have a good understanding of all the simulations I'm about to try to show you. So let's start with something very basic. I'm going to share my screen again. And this is supposed to be I do, and also if you finish it up, you'll get credit. You take care of your do now because you've filed a report with the solution I'm going to provide later in this video. So I think you can see my screen. I'm going to stop it and share it again because I want to be sure. I want to get this right in one session. All right. So let's go here. in advance, I did some preparation to set up what Ohm's law is about. Now I can show you some pictures. Some students have said they didn't understand, but I think the responses I got from students seeing me do it by hand gave them some motivation to do it, and they typed it up and got it right. All you do is change the numbers and use what I gave you for notes. In college, you will not have the exact problems. That defeats the purpose of your learning, and this is all I'm training you for. I've even had some students saying I'm doing the most because I'm not doing the problem and letting them regurgitate it. No, I gave you a similar problem. Now you try my technique on that problem. It's kind of like martial arts. I taught you how to punch and kick. Now knock down that wall. But not everybody understands the significance of, critical thinking. There's a difference between knocking down a wall and knocking down a wall. Anyway, so you should see what's on the screen. Voltage is equal to the current multiplied by the resistance. What's important, and when I do my calculations, because I knew when I was doing the calculations over the weekend, I was like, there's no way they're going to understand the dimensions, because we talked in prior weeks about dimensional analysis, which was important for your fractional or percent or just ratio calculations, how to cancel out things. I started this discussion off with how do you take your age from years to seconds? It wasn't a parlor trick. It wasn't me trying to give you tedious work. It was just try to show you how these buildings that we live in, how these structures that stand so tall actually withstand the elements of nature. And it's because of mathematical calculations. That is why STEM is so important, because it requires a lot of critical thinking. You can talk about it. You can't fake science. That you did bad science or bad math, it'll fall apart. And we have a lot of innovations that prove that science is a worthy tool. So let's get into it. If you see here, I don't know if you can see my mouse, this big V is not big because I made it that way. It's because of, the PhET simulations. And PhET simulation comes from, I think, Colorado Boulder. When I was in undergrad doing Noise Scholars Program, I was introduced to this, and I even used it with my students as a means to help them with certain science concepts that are taught in a science classroom. I'm not sure what's taught outside the classroom, but in the classroom, there are certain boundaries. So we have to work within reason, right? So for instance, the voltage is, illustrated by each of these battery cells. Now, if I increase the voltage up, you will see I have 1, 2, 3, 4, 5, 6 battery cells. If I bring it down, what do you think is gonna happen? And that's 0.1 volts. So basically, I have no batteries, but I want a little bit of a battery, so I can do that, right? So it's variable. So as I'm going through, I want you to understand what I'm doing. Now, I don't know if you were noticing earlier, as I changed the voltage, it was equivalent to this proportionality here. That is the current here, right? And that's his own law. V equals IR, well, some people say some other things, but V is equal to IR. I'm gonna say some other things, something about engineering, IR squared, right? RMS or something. But no, honestly, resistance is measured in ohms. Now these are the dimensions. So as I go through problems, voltage, this is for the students in all classes, because we're doing physics across the board. But physics 3 and 4, you guys are like the basic students. Robotics, you're like, you're a fellow, you're, I won't say fellow craft. You're an apprentice, you're getting it. And then computer science, you're a journeyman. So this is where we're going with these topics, right? So if I increase the voltage up or down, you'll notice that the current changes, right? So what's the dependent variable? That's the resistance in this case. Now watch what happens when I manipulate resistance. What changes? Notice the voltage didn't, right? And this is that concept, that's what I like about these simulations, because some people are visual creatures, about how the resistance and the current are proportional by their multiplicity, or their product, I should say. So you see what happens here. I want to pay attention to how this works as a circuit. Later on, we're going to be talking about parallel circuits. Now, parallel circuits make up 90%, if not more, in complicated circuitry of households, your cell phones, your TVs, laptops, so on and so forth. So if I change the resistance, you notice, right? Only the current changes. Now, resistance is supposed to be a means of controlling the actual current. Notice it's real simple in physics what it's called. It's called resistance. So let's continue on, right? I just want to show you everything. And I can show you the balance of everything because I made notes. So earlier I tested this theory with a student and I was like, find a balance where V as a icon here is equivalent to I and equivalent in size. So all of them look about the same size. All right. So let's go into this because this is really getting into, we started with dimensional analysis, that's basic mathematics for physics. And then we moved into work and energy. And, we touched on kinetic energy and I thought potential would be the same thing. So now we're moving further into, because I have robotic students and computer science students thinking about. So most of the physics students, you just got to worry about the physics calculations. But the hands-on projects that's coming up, it's going to require some understanding of some basic physics for you guys to accomplish them in computer science as well as robotics or career technical education or whatever you want to call it, pre-engineering. Okay, so let's jump into it. Now, I think the calculation for a balanced equation was about 5 volts. So it brings the V down to what I need it to look like. I need 5. Okay, 5.2. So the V looks about, same as this size, but now I got to fix these two. And then the current I measured would be adjustable to about, well, I got to change the resistance to get the current right. So that is, let's go up to 147 is what I said. That's about close. Can't get that 7. All right. But I think you get the gist of what I'm talking about, to keep them all, in a nice balance. And another thing is this is a series circuit. That's why I like using these. So the red mark or red vector, the red arrow shows where the current's going. This is a load. This is a resistor of some sort. Now, what is a resistor? I'm glad you asked. I sat down and prepared this. Later on, I'm going to show you a simulation. And the resistor looks like this. Okay. And it has a color coding. Now, the resistor is also known in engineering as a load. So a load could be a light bulb. A load could be, I don't know, a diode. It could be a capacitor. That's something draining down on the current of the system as well as the voltage. So, and the voltage is only pushing the current through. I always talk to students about how current flows. We're going to talk about that shortly too. Think of it as water that's flowing through a system, right? But it's electricity, basically. That's how it was explained to me in school. So this red mark represents the current or electrons that are passing through, measured in coulombs. And then there's some resistance. That resistance represents R. So it will travel further through a wire, which is like any type of conductor. Water is a conductor. That's why you shouldn't step in water when there's electricity present. I mean, you might get cooked. The battery is where the source of energy is coming from. And later on, we're going to talk about electromotive forces. But only a limited amount of time, so let me get through this. So the next thing I want to show you is exactly how these currents flow. So I took a little time, put this quick little blueprint or schematic together in FET, and FET simulations as a whole genre of tools I can use to teach students. So it's free software. Please donate if you can. It comes from Colorado Boulder International Science Foundation. I think supports them. But it's been helping me for almost 5 years of teaching. To illustrate what's going on inside of a circuit so students understand when they use conductors like copper. If you can see that, this is a copper inductor I was working on for a different demonstration of my robotic students. And then what happens with batteries. And the batteries come in all sorts of types and sizes. And if you're clever enough, you could take 2 batteries, these are not the same sizes, and you could generate current, which like I showed you earlier, and because they're connected, they will conduct around another wire and a resistor, and you'll see this, and you should see this in an illustration that I made earlier, hopefully. So we have our wire, those are conductors. We have our batteries, and I go through this with students every time so they can get a good understanding of what happens inside of electronics they use every day. Light bulb, resistor, you got a switch cuts it off. So these electrons that you see flowing through, they stop. So it's kind of like what you utilize in the house where you hit the logic 1, you hit the button for on, everything's on, electricity's flowing. You switch the switch downward or whatever orientation may be, and now you have a logic 0 and everything's off. That's what a switch is. And then as I go through with robotics and computer science students, you have other forms of conductors, switches, or things that just, you know, might react a different way to electricity, okay? So all that to say, the do now for tomorrow is going to go into, because I'm going to demonstrate the problem in this video as well. So that's why it's going to take some time. You have a battery source, you have a resistor, and I'll send scans of my notes just in case there's some people that like to just read it and don't. I've heard that from students. You know, okay, I didn't understand nothing you said in the video. All right, let me send you notes. So this is why I'm doing that. So I'll send the notes because they're all done in a later at a later time. But let me get to the visual students I have in the classroom, and then I'll do that. So the resistor, I want to point this out when I send my notes. This is called the cartoon version. If you want to be an engineer, if you want to be a technician or anything like I've been in my past, you need to understand blueprints. This is essential. It tells you how a system works. It's kind of like understanding the anatomy of electronics. So when I was a technician, a copy tech, what I did was I would ask for the blueprints of a particular machine and a service manual. So when I got on site, I would know what were the solutions, how to troubleshoot, and how to fix things. And that's based on bulletins and collaboration, which is another, you know, scientist type, you know, technical type of atmosphere you need to get used to. So if I switch to this view, you should see what's called the schematic view. Does it show that? No, I thought it would show a little link. But this is the cartoon view, and this is the schematic view. Now notice the battery looks like this. Let me go back up. So we got a battery that looks like this symbol, right? And I might just draw out symbols and put them on a piece of paper and be like, for extra credit, which are these symbols? So pay attention, like, what does this symbol mean? And what is this symbol? And it'll be like handwritings, like hieroglyphics. And you should know from watching this video what they are or practicing with the simulation. And I can send you that link if you want to, because it's a free service. So light bulb, that's what that's going to look like. And we can talk about that later. Resistor, switch, and other objects. Notice how the other objects are resistors. Right? Hint, hint, how do they operate in your circuit? Dog, these are loads, huh? So I could put a dog on there, and are you getting an idea what I was talking about? How you could be in water and you're a load? Dog, hand, pencil, current, travel, heat, cook, rotisserie. All right, so I'm glad you got that. And then the last part I want to talk about before I switch screens, let me go back to the cartoon mode. Before I switch screens is how do electrons flow in representation to the traditional flow? So what I want you to flow, if you ever had, what I want you to designate, if you ever have to draw something for me for a free body diagram in terms of electronics, just use this diagram where the electricity is going in this direction of current. See the arrows make current? That's all I want you to focus on. You will have some people who are in industry and they will tell you it goes this way. For credit in my class, just focus on the conventional, okay? Because that question has come up from some, you know, very savvy students in the past. Now, I covered that. What else is there? Oh, I want to get into this generator thing. So give me a moment. Let me unshare because I want to make sure I got the right screen. And share. Okay, I want to be sure. Okay, I see it. So here, I'm gonna go back and always ask students a couple of questions about this simulation. Always like, you know, if I turn on, I was like, well, you kind of seen it early from the video, but because I had it running beforehand. Be like, you know, if I turn on the water valve, why is it this light bulb works? And a lot of them spend time on that, and it's even become an extra credit session. Like, okay, really, really look it up, and they'll get on their Chromebooks, they'll investigate, and it still baffles them. So then, if you flesh this out a little bit, on this wheel, which is used for like sailors and decks, but just imagine this mountain to something. It spins because of the current flow of water. Now, remember earlier I talked about current, V equals IR, Ohm's law. So we got I right here. straight current. Now I can increase the current flow, but notice even with low current flow, the light works. Now I want you to keep in mind, you see the pulsing right here? I want you to keep in mind the video you just watched. And in terms of the bicycle, electromagnetic forces, light, what is light? That's electromagnetic force. And that equation, Maxwell's equation, that's one of my favorite equations that I had to study when I was at CERN. So look, let's investigate this further. And we're in the generator section, and you can review this on your own to come up with a better response, robotics and computer science, and kind of give you a hint where I'm going. So it's rotating. For lack of a lesser term, let's say this is oscillating because it's going, if you look at 180, let me stop the water. And if you look at the magnet as your reference, say this is 0 degrees, this is 90 degrees, 180 degrees, 270, back to 360, right? So that's for the computer science students. But if you have it rotating from 90 to negative 90, and it keeps doing that, that's a form of oscillation. So hint, word of the day term I might use. Well, word of the day is for the school, but term of the day, that gets you credit in my class. So let's turn the current back on. And give it a little bit more current, hint, I. And I get more light, right? See it pulsing? And this thing here is called a compass, a magnetic compass. And these little dots right here represent electrons. So this is a higher level term for the robotics students I have and the computer science students I have. But hold on, the question I ask you all is, with no wires connected to this, how is it that this system works to provide light? Just doing a little bit of wait time. Okay, so let's reveal some parameters. The Earth itself has what is called a magnetic field. And what's behind me is what is called, if you see the virtual background, because I don't like people seeing in my house, the aurora borealis. Okay, so the aurora borealis allows us to see a wonderful sky once there's something called a solar flare or corona that hits our atmosphere. And what happens is that green sky that you see like behind me, or if you're north enough on the Earth, that's the dissipation of radiation, right? So it's one of the most beautiful things to see. I've seen it once or twice in my lifetime. Now, with that said, imagine right now, not imagine, but try to visualize that there is a magnetic field all around us. There's a reason why you can have two magnets and put them nearby, and if you follow the laws of magnetism, they'll either attract or repel. That's a different discussion. So, show field. Now, if you pay attention, you should see all the diamonds in the background, right? And these diamonds, when it's called diamonds, these red and gray angles or connected, or sections of a diamond, they're rotating just like this wheel. And there's a magnet attached to this rotating wheel. So it's constantly changing the environment, which is the magnetic field around it. Yes, Matt. 1 second. Okay. Okay, sorry about that. I had somebody contact me about a later engagement. All right, so I think I'm still sharing, right? Share. Okay, good. Okay, so am I muted? No, I'm not muted. Okay. So that's that thought right there. The next thing you want to look at is basically where was that at? And say that back in my computer science students, but the problem itself. So let me minimize this. I think I've covered this, great. Not so bad, not so bad. So the do now is dated for tomorrow. And that do now, it pretty much should be in this Google form, right? Now I'm gonna start you off, but I'm only gonna do one portion of it, but there's more sections that you would include. I'm not gonna do the entire problem because this is a Sunday and I still have things to do like wash clothes and stuff. But I wanna get this out to you in advance so you don't feel slighted. We have midterms coming up probably Friday, just to get it out the way, because we're gonna end in this quarter somewhere around June the 16th. So I gotta get my grades done probably like June 12th. That's just me. But I need you to pay attention to everything I'm doing on EDSB because grades are coming to a close and then we need to think about next year or summer school if that's possible. So what you want to start off is what I hope you see. Shared document. I'm gonna check one more time because I'm looking at the clock and I'm running out of time. So let me share the screen again. Okay, I didn't know I could do that. I could share it again and just check and I stop it. All right, so you should be shared because I just checked the feature in here. Let's go to the problem. You start off with a header, right? So your header is, of course, your name. I'm gonna type my name. The next thing, of course, you want to do is give me the date. Now, this is everything I'm telling you need what's inside the header. I've already started you off, and don't forget about this. I've done this in other videos. You need to type in the title of your document so that it saves and you can find it on your cell phone, your laptop, or whatever device you're using. If you don't do this, it'll come up as untitled and it'll be hard to find. All right. So what do I have? Today's date. Well, I'm gonna date it for the 18th, which is tomorrow. And this is your assignment for tomorrow. And then, of course, which period. I've posted this as extra credit for all of you guys. So this is near to my robotics and computer science students. I'm just going to say robotics. But this is pretty much for all students. So don't like direct message me and say, well, you did it for robotics, so I ain't got to do it. No, I did it because a lot of y'all are taking time to do the work. So you should do it too so you can get some extra credit, all right? Or you can at least get something to help you. So what was I saying? We got the title. Robotics is, and don't forget to say the period number. I think robotics is 5th. Period. And yes, you're to type period. So yeah, I'm trying to get away with just doing less. Now, to get maximum credit, I do need to see all steps of the solution I wrote out that I will scan and send out tonight. If you don't have all those things, please do not message me coming to me talking about, well, why did I get 65%? I did everything you did. No, you wrote down only the solutions. You can write down the steps. And with the steps, I'm helping you develop what is called a portfolio or at least an engineering notebook for you to refer back to in your terms of your work. Everything you have, I have you do in Google Docs because it starts you with a repository of notes. This is similar to an engineering notebook, whether you know it or not. So with that said, let's jump into the problem. So that's what I'm gonna say yesterday. Tomorrow's problem is going to involve, let me see if I can do this way. This here. So I'll start off with the problem and go ahead and take it from here. You can highlight what's necessary. And then I'm gonna go back to my document and I'm gonna post it here. Okay, that's the first step. A lot of you guys are not doing that. You're giving me a page of solutions. Listen, I'm from the old school training, and I went to elementary school. You need a formal document which required a header, the problem, and then you solve it. Okay, this taught you how to generate reports in all walks of life. So if you're not doing the bare minimum, don't be expecting a high grade. You're just trying to, slip through the cracks. Please don't do that. So let me read the problem to you. A circuit consists, and we talked about circuits earlier, of 3 resistors in series, all right, to a 240 volt battery. And I just want to make sure that my headset is on the right setting for volume. So the current in the circuit is 0.0328 amps, as in amperes. Given that R1 is equal to 287.5 ohms and R2 is equal to 148.7 ohms, A, It's part one. I separated because the problem that I pulled from my archives was all together as one. So A, so to help you focus, find the resistance of R3 and let you know there's a part two, right? B, the potential difference across each resistor. Now I want to quickly discuss potential difference. Now potential difference is known as something as electromotive force. Electromotive force is the electromagnetism, as they show here in this document. It's wiki, I know, but you can look up any article. Wiki, I mean, I've been using since I was in Grand Valley State University, and I hate to say it's a quick reference. I know it's constantly re-edited from some of my educated friends, but it's a quick reference, right? So you can find better resources, send them to me. I'm doing a one-man team here. So in electronics, more especially, you can talk about EMF. And in this problem, they're going to be talking about EMF. There's a symbol that's denoted as this here. It's like a little calligraphic E. And in my notes, you're gonna be like, "What is that, Mr. Tyler?" That's EMF. And when I write it down doing the math, I'm not writing EMF every time I'm doing a derivation. I'm writing that little E. So I just wanted to make that quick little note so y'all don't get confused with the scanned documents I'm sending to your student portals for extra help to finish this problem. Let's see here. So let's jump into it. What do we need to solve this problem? And I'm gonna do part A with you. I'm gonna try, because I'm looking at the time, do part, because I got other things that I have to take care of, other obligations I promise. So we got, yeah, I'm gonna do part A a little. I'm gonna do all of part A. I'm gonna try. So, because I already did it by hand, I'm gonna my hand hurting, and I gotta type it. So, basically, you want to set up yourself with the equations for what to do. So let me go back here to the notes, and I know already I'm gonna start with Ohm's law, right? So Ohm's law is, so part A. Start with Ohm's law, and I kind of showed you Ohm's law earlier from when we was working on changing the values to set up the equation, right? So I'm trying to figure out how I'm gonna write E. That's why I was like, what did I do? I just put EMF across all the, yeah, because I wanted to take account for the computer science aspects. So start with Ohm's law in terms of EMF, which is our potential difference. Now, potential difference, you could say, is our voltage, right? So with that said, and this is when we have electromotive forces involved. So this is, you know, a pretty high-tech gadgetry. When you're doing equations in terms of circuit analysis and they involve EMF, you're dealing with like something that has a lot of electronics that have transformers and generators. It's just to be known. But you're dealing with a basic circuit that has, say, a 9-volt battery or however volt battery is DC. You're not really worried about it. You just call it volts. So don't get confused, okay? I want to make that known because I know that can go left. So with that understood, you can just summarize voltage, V equals IR, and I'm using Ohm's law, is basically, and I mentioned this earlier, the same as saying EMF, or electromotive force, is equivalent to I times R. Now, what does that mean? Later on in our problem, EMF is going to mean, because we have three resistors we have to account for, and we have to find something called resistor equivalence. So EMF is going to be multiplied by the current, it's going to be equal to the current multiplied by our REQ, or basically known as, let me just type it out, equivalent resistance. Okay. And this is current, because I'm not giving it justice by not saying what it is. You might not know what I'm talking about. I can just do this. So I want you to know what's going on, even if I have to go. I'm gonna be late. All right, and this is voltage. All right, so I want you to know some key things there, and if you have this all in your notes, you will get extra credit for it because this is I'm developing you, so you got to put this in there, and you might need it on other tests. We have a midterm coming up, and then we have a final coming up. So having these things typed up is not me torturing you; it's just making you archive it when you need it on that test, because you're not going to get any videos or any scanned submissions from me on that end. You're going to have to try this stuff out. So I think you see what I'm doing, right? Potential difference was EMF, or I should say, or what EMF is, electromotive force. Okay, so I think I fleshed that out for you. Now, those are things you got to understand. Okay, I'm gonna do like the physics book did. Strategy, call this section that. Okay. Now, and I should have put current there too, huh? So now that we know that some of these basic parameters, we're missing one big thing. Now, our equivalent resistance, I don't know if you remember what this is about, and I talked about it for some of the students with some, time where I felt that I had to probably flesh that out again because you might have forgot about it. But equivalent resistance, why am I typing it again? Let's take that. I saw another error up there, I gotta fix that. Is equal to, I said it right? Yeah, it started with Ohm's law in terms of EMF, or yeah, I thought I put an of right there. Okay, I didn't. I did that right. So equivalent resistance is equivalent to, sounds like a run-on, don't it? Resistor 1, right, plus resistor 2, plus resistor 3, plus however many other resistors you got going on in there in a series circuit. Let me be very, very clear about that. We're talking about within a, not within, series circuit. All right. So we're just some notes about how this system is going to work. Now, the problem very specifically is showing you what I showed you earlier. Let me come back to it for a visual. This type of circuit, that's why I drew this circuit out. And you'll see this in my scan notes. There's like a little box. You can't see it because of the visual background, but I'll scan it. And it goes around in a circle. I mean, a box. And this is a series circuit. Now, if you had connections and junction points, which separated it up, then you would have a little more, wiggle room. So let's get into it. Where is that? Here we go. Just want you to see that so you know where I'm going with this. So we're basically going to look at how to take all those resistors out of the circuit and replace them with one resistor, I'm sorry. And what does that mean for us? Well, that does mean we don't have to purchase many parts. We don't have to do all sorts of crazy things. But with all that said, let's get back to this problem. Now, knowing this, I need to establish some known unknowns. I need to know what I'm working with because I know which tools to use. And these are some of the tools. Okay. Let's just do that. These are some of your tools. So these are things I want you to, remember in case you forgot. You can say it's resistance or equivalent resistance based upon need, and that too. Okay, so where does that leave us? We need to understand or ascertain what our known values are. And again, I told you I'm going to use this throughout all of my physics courses, even especially my upper level courses, what your known and unknown values are. So what do we have? Well, our EMF, the problem told us, is what? Come up here. Is going to be, let's see here, that's basically the resistor series of a 24.0 volts battery. What's our EMF? So it's going to be 24.0 volts. What else do we know? Well, we know our current, right? It's I. And that's equal to, and maybe I should say current so no one gets confused. And in my problem, I will specify I. Again, I'm not writing all these things down. And I'll have the little fancy E that goes here for EMF. But let's see here. The current in our problem is 0.0328, and that's amps. Next, we have our resistor, 1, they gave us. And that was equivalent to, and I'm putting this down for my notes, but again, this is given in a problem above, so you don't get confused. So that's going to be basically 287.5 ohms. And that's our resistor. You could write omega or ohms if you're fancy, but you can just put ohms so you don't say you get confused. R2. What was our R2 again? Our resistor number 2. That was 148.7 ohms. Okay. Next, what is the question asking us? Well, it looks like that's going to be, because we had 2 parts of this problem. In part A, we had, hold on, we had R3 that we had to find based upon what the problem gave us. So put question mark something in ohms. And then in part B, we have what? Well, let's go back. We need to find, come here, part B, the potential difference across each resistors. There are 3 resistors. So what I suspect, we're going to have to use our equivalent resistors to figure out what R3 is. Next, we're going to have to use that to figure out what the voltage values are, or the potential differences are on each of the 3 resistors. So what do we got to do? We got to find 3 voltages. So V1 is measured in volts, but what is it going to be equal to? Should I do it that way? I should do it this way. We have to find V2. That's going to be measured in some type of voltage. I want to do it the other way because that's how I did it in my notes. So some number volts. I know how I want to do it because it's going to reflect when they see my notes how I did it. That's V2 is equivalent to some number we're going to calculate in volts. And then lastly, and I might just do a video tomorrow doing part B, but I want to get at least part A out the way. I am just trying to be proactive so I can have time to do other things. All right, so that is everything as far as what we have to find part B. We have to find the potential difference, voltage 1, voltage 2, voltage 3 across these. And I'm going to, for this moment, because I think it's pretty quick to do, finish what is necessary for part A. Now, again, this, from the looks of it, takes about 4 pages to do. So this is why I need a 2-part thing. Otherwise, it's going to take me about 2 hours to finish. But I'm at the end of my time, so let's get into the problem. So looking here, I see that I need to use what? Well, I remember I mentioned Ohm's law. So this is the system. We have resistor 1, resistor 2, and resistor 3. Right? And this system is not the same as the system we have in the problem, but this gives you a visual of what's going on. And we just try to find out what's happening here at resistor 3. Right? And the potential difference, I didn't measure it correctly. I should have did it this way. There we go. The potential difference, this is how I use a voltmeter. And a voltmeter, where do I got it at? It's one of these that I've had you guys use in class. They come in different sizes. You know, so it allows you to test the resistors as needed and find out what's going on in your circuit. So that's what this is on the screen. But honestly, you're going to have to calculate what you don't know about resistor 3, because I didn't give, well, that value wasn't given in the problem. So let's go back to it all. we got to use Ohm's law here real quickly to figure out what's going on. So that is, I'm going to use EMF, and remember that's voltage, in terms of Ohm's law to calculate our resistor 3. So that's going to be our EMF. If you remember, electromotive force is equivalent to our current I multiplied by our resistance. We'll take that a bit further. You could also say that EMF, and I mentioned this earlier in the above description of what you need to know in the bullets, it can be equal to the current I multiplied by your REQ, or your equivalent resistance, right? So another value of A you got to find is what? Your REQ, right? So you put that in here so you don't get confused. See if I can do it that way, because it's going to take some editing. REQ question mark ohms. Those two go hand in hand, right? Because it's going to allow you to find R3. So let's get into it. So our REQ, or equivalent resistance, is there. We know what equation we need, but now we need to solve for REQ because it's still being multiplied together. So let's use some algebra here. Okay. I'm going to take this here, copy that, put that there. And what do we got? So EMF, electromotive force, is equivalent to the current multiplied by the equivalent resistance. All right, so what does that mean for us? Well, we need to do some algebra to solve for REQ by itself. So I'm going to divide, because if you notice here, right by the current, it's a multiplication process. So that's the same as saying, what is the opposite of multiplication? It's division. So give me a second, I'm going to set it up for you. And I'm going to divide by what I don't want next to my REQ, or equivalent resistance. That's current. So I can say, hey, what you do to one side, you got to do to the other. And that allows me to cross cancel this situation out. So let me copy this again, and then come down here, and I get what? Well, my I will cancel with the I underneath. So let me format that out. And this I down here will cancel with the I above. So what is our new equation at this phase, right? What do you see now? Well, let me replace what's there, and not replace what's there, but let me rewrite what's there. So I can actually delete this. Okay. Delete that. And delete that. Take this. And move all this over. Because the new equation is just, I'm just writing it the correct way for mathematicians and scientists. And let's bring this over here. Now, if I come over, I want equal, and equals what? That. Ah, goodness, it looks bad. Right. So that's not one that's current, because I don't want nobody getting confused. I want it to be like an L, but it didn't do it. Oh, no, it's I. That's why I didn't do it. I'm thinking about something else. Doesn't take the L. So there's your EMF, right? So EMF divided by current gives you what you need. Put the values in. And I end up with what? REQ is, or equivalent resistance is, equal to what? Let's put the numbers in. That's 24 divided by our current, which was given earlier, 0.0328 amps. When you calculate that out, you get a new value of REQ equivalent to 731.71. Oh, 71 ohms. Because remember, this is equivalent resistance, so it's got to be measured in ohms. Okay, so we're almost out of the woods, right? So let's go here. Just want to make sure that's known, because we got to come back to that, because you're going to need that answer. All right, so what do we do now? We're going to take this REQ and we're going to put it back into perspective with what we need. Remember earlier I said that, where did I put it? Where did I put it? So equivalent resistance is this. This is your REQ basically, in case you didn't know what I was doing there. And it is equal to this situation here. Now we found it because we had other values and not it. And we had current and voltage to do it, or EMF. But now we got to look at this again. So remember, let's underline that. Remember that. This is tripping. Okay. Remember that. That is that, right? So next, we need to understand what we're looking for, right? And that's that second part of it, the R3. That's why earlier I said, hey, we got to find REQ before we can find R3, because we can do some algebra to find that too. So there's a lot of algebra in this problem, so don't get frustrated. I just told you it was coming since 4 weeks ago. So I'm going to take this, because we only got 3 resistors. And we're going to say what? Well, we know this is the equation to find equivalent resistance, and it would go to R4, R5 if you had more resistors. But we only got 3, so this is the proper setup. But now we're going to use some algebra to solve for R3. So now, solve for R3 using some more algebra. So what does that look like, right? I'm not going to use arrows for this because we got to do some things. Well, I know that I want to remove I want to remove R1 and R2 from the situation. So they're addition prospects, or not addition mathematical operations. So I have to do the reverse addition. That's subtraction. Remember, algebra states what you do to one side, you do to the other. So I started here, and then I think I could do this a long way. I can say, hey, I'm going to subtract R1, and I'm also subtract R2, because I want to just have R3 all to myself. Right? So I just want to let you see the changes and what happened. Right? And likewise, you got to do what you do to one side in algebra, you definitely have to do to the other side of the equation. Okay, so it just shows you how that equation changes in one step. Now, addition subtraction is easier than multiplication division, because you got to do some fractions or you do that stuff. These operations are pretty, straightforward. So maybe I can do some arrows. And I'll change the color in a moment. So the arrows just mean that these are steps that you should try. Okay. So what does that mean? Well, some things will cancel out and leave what you need to find R3. So give me a second. So now we end up with a new equation of R3 is equivalent to, what do we say, this equation here, because we found our REQ earlier from doing algebra earlier. Right? And over here, these two will cancel, just so you can follow along. You're like, what happened over there? I'm going to show you. And my dad would say, I'll show you better than I tell you. That cancels, right? And then all this here is going to cancel too, just in case you missed that step. All right? So now R3 is by itself, and that's why I wrote it that way. Okay, so what does that mean? Let's finish the problem off, because I'm only doing part A. Tomorrow, if need be, I'll see how you guys do on this much. I'll present a video on the very last part, which is part B. So R3 is equal to, at this point, you did most of the work, so you just enjoy the fruits of your work, your labors, and you plug in the values. That'll be negative, don't forget, that's negative right there. And then parentheses, what did we find earlier for R1? Well, I don't feel like typing everything up. I just go back to why I did this setup. So that was R1 from earlier, right? Let's come here. And then this is going to be minus what else? Well, R2. So what was R2? This is why I have you guys do all these steps, so things are easier for you. So set of parentheses. And then we're going to add what we found earlier, right? Where is that at? Well, we said it was this number here. Okay. No, come back. There we go. And I don't need this to be bolded. That was because that was one of the solutions you needed to get to this part. You're not. I'm going to say you're not going to do what I asked you to do, computer. All right. So with all those together, I did a quick calculation already. You can use Google to check my answers, but where is that thing at? Where did Joker go? So R3, once you combine all this correctly and you follow your order of operations, should be, let's see here, one last bullet. And this is R3 is equivalent to what? Well, from what I gathered, it's 295.51 ohms. Okay. And that's as far as I'm going to go for today, because I want you to, digest this in segments. So there'll be a part 2 to this video tomorrow, probably sometime around, I want to say 9 a.m. It should be ready for you. And I'm going to process this much because I want to make sure, it's stress tested and sent out in an appropriate amount of time. But look at this video, go through it, come back to it. And tomorrow I'm going to go through the second part of it, which is the last couple of steps to part B. All right. But you should be trying to develop a document with part A stuff in this video and just be able to open the document tomorrow when I go through this and fill in the rest to finish the assignment. All right. I hope all you guys are staying well out there. Science is a continuous progress. It's something that keeps the mind sharp, especially during crisis. So practice, utilize it, and try to get some of this stuff done. June 12th is the best I can tell you when all grades will be finished on my end. Please get in there in all your classes, not just my classes, and finish your work, all right? Stay safe out there in Zen.